Okay. Number 12. We're going to find the stronger acid in each pair. And I've got first pair is HBr and what's the other one? Cl. Okay. This is a binary acid. The binary acid, like of the halogens, with a binary acid where you've got hydrogen and just one other element, it's going to be, the acid strength is going to be determined by the bond strength to hydrogen. The weaker that is, the stronger the acid is, the easier it is to get it to dissociate. This is a case where size matters in an inverse way. The bigger a particular, the bigger of the non-hydrogen atoms is, the weaker the bond is, because there's less overlap, less favorable overlap. The hydrogen is just an EB thing, and it doesn't overlap as well. You know, the huge orbital. And so this, what happens to size as we go down?
Increases.
Bigger. So bromide is bigger than chloride. So bromide bigger than chloride, this is the stronger acid, since Br is larger than chlorine. Okay? Now, for number B, okay, perbromic acid versus hypobromic acid. Versus, is that the right one? Yeah. Now, in this case, it's not a binary acid. It's what we call an oxoacid. And these oxoacids have the same, the other element is the same. So this is equal, and the hydrogen is equal. So we're going to look at what is going to give me the more stable anion when it dissociates to give me the acid, the hydrogen ion, and whatever the anion is, the conjugate base of the acid. And that turns out to be proportional to the number of oxygen atoms. The more oxygen atoms there are, the more that anion can delocalize its electrons and spread out that electron density for the negative charge over all the oxygen atoms. So the one with the most oxygens is going to be the stronger acid. And so in that case, this one, more oxygens. There's this more. More. There exists more delocalization. Of electric charge. And the anion. And so now I would expect the perbromic acid to be more powerful than that, or stronger. So C. It's stronger in terms of it's going to be more dissociated. It's going to be dissociated. Now H2SE versus H2O. Again, this is a binary acid. Which one's size matters? Which one's bigger?
H2SE.
So the
Yeah.
for the same reason.
So the amount of hydrogen on it doesn't matter?
Well, they both have the same.
But if it was different, like, would it matter?
No. This is a binary acid, and so so selenium is larger than oxygen. And now D. I have ammonium versus arsonium. And again, it's binary acid. Which one's bigger? Arsenic?
Yeah.
Yeah.
Okay, so that means this one, because arsenic is bigger than nitrogen. And last but not least, we have, okay, perbromic acid, not perbromic, hypobromic acids versus hypoiodic. So I have H versus H. Well, now, all things are equal in terms of the number of oxygens and the number of hydrogens. What is different is the heteroatom here, bromine versus iodine. But they're in the same group. That's the key. So at this point, we're going to look at the stability of the oxoanion of the conjugate base. And that's going to be more stabilized by a more electronegative. The most electronegative of the heteroatoms is going to be the one that's going to favor it. And which one is more higher electronegativity? Bromine or iodine?
Bromine.
Okay, bromine.
Yeah.
Because it's a size effect. Remember, electronegativity increases as size decreases. We can go back and discuss that a little bit later.
But like
This is more electronegative, so this would be the stronger. Br, more electronegative. Okay? And those are the effects that you want to take into consideration when you're discussing the strength of a given acid, your a priori prediction. Yes?
The stronger because it is lower than the bromine.
Yeah, it is bigger than the bromine, but electronegativity increases with decreasing size. So the smaller atoms, remember the most electronegative of the elements is fluorine. And because as we proceed to the right across a row, we get smaller.
Well, wouldn't that be the same for the first acid? I mean,
yeah,
that was the
that's
first
what
one.
I would say as well.
Well, because these were not electronegative. This was size and the bond to hydrogen. These are oxyacids where the hydrogen is not attached to the bromine. The hydrogen is attached to the oxygen. And so we have to take into account the stability of the oxyanion that forms. And this was true in the when it was the number of oxygens was the thing that predominated because it's more delocalized over all the oxygens. The oxyanion is more stable. In this case, it's because this is more electronegative, and so it's going to stabilize that negative charge. Because it's going to attract more of that negative charge. It's going to make it more stable than this one. So yeah, that is, in fact, that's part of why I asked the question this way. We're testing for those things. These are effects I'm going to discuss on Tuesday. I got a lot to talk about Tuesday. Okay, so is that a wrap?